In this video, we're going to begin our in-depth discussion of trigonometric identities. So we've actually used identities quite a bit so far. So for instance, anytime you evaluate a cosecant by taking the reciprocal of sine, you're using an identity. So an identity is just going to be a relationship that's true regardless of the input you supply. So as long as it's defined for the input you supply, it's something that's going to be true no matter what. You can kind of think of it like a definition. So in some ways we think of cosecant as being defined as the reciprocal of sine. So the relationship between those two functions represents what we call an identity. So we're going to use identities in slightly different ways from here on out. We'll use them in more, more open, more abstract ways, and we'll also use them in very concrete ways in order to evaluate trig functions for some of the values that we haven't been able to evaluate so far. So every time we've evaluated a trigonometric function so far, as long as we didn't have a calculator, it's always been applied to some angle that's a multiple of 30 degrees, 45 degrees, or 60 degrees. Well, of course, there are a lot more angles on the unit circle and existing in general than things that are multiples of those three original angles. So identities are also going to allow us to evaluate trigonometric values for some of those other angles that we don't see readily identified on the unit circle. So here we're going to focus on using our identities to simplify expressions containing trigonometric functions and also to prove other identities. So using established relationships that we already have, we can then prove other more complicated relationships among our trigonometric functions. So let's start with simplification. Suppose we have an expression that involves potentially more than one trigonometric function. We can use some of the identities we have so far in order to simplify expressions that have those functions. Now we have some limitations involved when we're talking about simplifying. So we have to be careful about what we do when we try to take something that's represented as an expression, not an equation, and then simplify it from where it currently stands. So when simplifying, we can only perform operations that do not require an equal sign. So what I mean by that is, if it's the kind of operation where you would have to do it to two sides of an equation to keep things in balance, it's not allowed. So for instance, you can't square something. Squaring something fundamentally changes the structure of the expression. So unless you're starting with an equation where you know two things are equal and you're squaring both sides, thereby balancing things, you can't just square an arbitrary expression without changing it. So squaring it will fundamentally change the structure of the expression. So something like that will not be allowed. Well, that seems to rule out a lot of things. We can't just add something random, we can't subtract, we can't really multiply or divide, because all of those kind of operations require that we do things on both sides of an equal sign to keep our expressions in balance. So if all of those things are ruled out, well then what can we still do? How can we simplify if we don't have all of those options at our disposal? Well, one thing we can do is we can take an expression and we can rewrite it using an existing identity. So if we accept that our identities express true relationships, then we can substitute one expression for another using things that we know are equal based on that identity. So for instance, anywhere we see a cosecant, we could substitute 1 divided by sine because we have an established identity that verifies the fact that those two expressions are equivalent to one another. Now another option we have, depending on the type of expression we're looking at, is we can technically multiply, but it's not going to be multiplication like we typically see. One thing we can do involving multiplication is we can multiply on the top and bottom in the numerator and denominator of an expression by the same thing, whatever that means. So we can multiply an expression by another expression as long as we're multiplying by an expression divided by itself, so something divided by itself. Well, why is that? Well, think about something divided by itself. What does that mean? Well, anything divided by itself is really equivalent to just 1. What happens when you multiply something by 1? Well, nothing changes. You have the same thing that you started with. So if you multiply a numerator and a denominator by the same thing, then you may change how the expression looks, but you're not changing the fundamental structure of it. Everything is still balanced, and you're still looking at the same expression from a logical standpoint. So strategies where that might come in handy. If you need to find a least common denominator, that takes typically multiplying on top and bottom by the same thing in order to get your denominators to match, in order to combine two rational expressions. There's also a strategy called multiplying by the conjugate of something. If we have something like a plus b, the conjugate of a plus b is a minus b. So in certain situations, multiplying by the conjugate of an expression will be a strategy we may use. And we can do that, that's legal, as long as we do the same thing to the numerator of our expression as well as the denominator. Because again, multiplying by one thing divided by itself is really just multiplying by 1, which doesn't change anything. Another option that may come in handy, another strategy, is factoring. So factoring is just rewriting an expression in a different way. So finding a greatest common factor, factoring that out, rewriting an expression using the difference of squares formula. Factoring just takes an algebraic expression and rewrites it in a different form. So sometimes factoring may be handy, particularly if we have, like for instance, a numerator and denominator, and we can find common factors on top and bottom that cancel out. Factoring may be useful. But notice all of these different strategies are not going to require us to do something on one side of an equal sign and the other side. Since we're not fundamentally changing the structure of our expression, we're just changing how it looks, we can make all of these changes without having to have some type of equal relationship set up at the very beginning. Now, if you're stuck, if you see an expression and you don't really know where to start, or maybe you've just gotten to the point where it just doesn't seem like you really have any other options for what you might do, oftentimes it's going to help to write everything in terms of sine and cosine. So when we looked at the unit circle, we discussed the fact that pretty much everything is related to sine and cosine. So if we're looking at the unit circle, anywhere on the unit circle, if you look at the coordinates at any particular radian measure, once you get to that point, the y-coordinate represents your sine and the x-coordinate represents your cosine. So if everything can be defined in terms of x and y, that also means everything can be defined in terms of sine and cosine as far as our trigonometric functions are concerned. So when in doubt, if you can't think of anything else to do, if you have other trig functions involved in your expression, maybe writing them in terms of sine and cosine may put you in a better position and may give you some other options for what you can then do. Now, keep in mind the term simplified is honestly kind of subjective. Simplification can mean different things depending on the goal. So in a lot of cases, simplification is represented by a specific goal. So how do you determine when you fully simplified something? Well, if there are stipulations for what the simplification must have, you have to make sure that you've met those requirements in order to say that something is fully simplified. So let's work through a couple examples and we'll see what the goal is based on how the problem is described. So here's our first expression. We want to simplify secant squared of x times cotangent of x times cosine of x. And specifically, we want to write the final form with no fractions. So ideally, we want to take this expression that has 3 trigonometric functions involved, and we somehow want to write it maybe with fewer factors, fewer trigonometric functions, and we want to make sure that the final form we give doesn't have any fractions. So if there's a numerator and a denominator, we can't leave it in that form. There can't be a denominator. We have to get rid of that before we report our final answer. Now, just looking at these individual functions as is, they don't seem to have much in common. I don't see anything I can do that's going to maybe cancel out one versus another. So this is a good time to just write everything in terms of sine and cosine. We already have a cosine here, but secant and cotangent can both be written in terms of sine and cosine. So secant is defined as the reciprocal of cosine, which means that secant squared is the reciprocal of cosine squared. So secant squared could be written as 1 over cosine squared. Now what about cotangent? In terms of sine and cosine, cotangent is defined as the cosine divided by the sine. And then of course cosine is just cosine. It's already written in terms of one of those fundamental functions. Now what's the benefit of writing in this form? Well, now we have numerators and denominators. Keep in mind cosine could be written over 1 so that we truly have 3 rational expressions. So the benefit here is anything that's a matching factor within the numerator and denominator reduces to 1. It divides out. So notice in the numerator, if we were to just rewrite what we have, clean it up a little bit, 1 times cosine could be written as cosine squared of x. And then in the denominator, we have a cosine squared times a sine times a 1. So our denominator is cosine squared x times sine x. So we really have 3 factors here. We have 1 factor in the numerator and then 2 factors in the denominator. So any factor that's common to the numerator and denominator reduces to 1. They divide out and reduce to 1. So notice we have a cosine squared in common, so that actually cancels out. Now what are we left with in the numerator? Canceling is division, so we have to be careful here. We're not left with a 0 in the numerator. When we cancel, divide out 2 things, divide something by itself, we're left with a 1. So we really have a 1 left in the numerator. So what we're left over with is 1 divided by sine x. And we know that this is the same thing as cosecant of x. So that is going to be the simplified form of this expression. And notice again it said write the final form with no fractions. So if we got to this point, we know we're not done. We can't leave it in that form. This is rational, it's fractional, we can't leave it in that form. But here we just used an identity to transform that 1 over sine into a cosecant because they are equivalent to one another. So that would be our simplified form. And it definitely is a lot simpler than the expression we started with. Okay, let's try another one. So we want to simplify the cosine of theta divided by 1 plus the sine of theta, that got cut off, plus tangent theta. And again, we want to write the final form with no fractions. Okay, well automatically I have a fraction to start with. We know that's not allowed. So that 1 plus sine, that's going to have to go away at some point. Now here is another time when maybe writing in terms of sine and cosine may be a good option. Because notice for this first expression, we already have sine and cosine. And then the next term we have a tangent, which could also be written in terms of sine and cosine. So a good place to start would be to take that tangent and write it in terms of sine and cosine. So the first term we can leave alone. It's already in terms of those 2 original functions. So cosine theta over 1 plus sine theta. And tangent is defined as the ratio of sine over cosine by definition. Okay, well now we have 2 rational expressions. Notice they each have a different denominator. So if we wanted to combine these together, we would need that common denominator. Well, our first denominator, 1 plus sine theta, our second is cosine theta. These denominators don't have anything in common. That means our common denominator is going to need both a 1 plus sine and a cosine. So for our first rational expression, we've got the 1 plus sine, but we're missing the cosine. So in order to rewrite this expression with the denominator we want, we're going to have to multiply on top and bottom by whatever it is that we're missing, which in this case is going to be the cosine. Now for this ratio, we're missing the 1 plus sine in the denominator. So again, we're going to have to multiply top and bottom by whatever we're missing. Well, now let's just clean this up. Now, just a word of advice. Typically, when you get that common denominator, you want to leave it in a factored form, at least for the time being. In order to get to your final answer, it may be beneficial to distribute it, to clean it up, but in a lot of cases, you'll find that you want to leave it in the factored form because you may end up with something that will cancel with one of the factors in the denominator. So focus more on the numerator at this point and just leave the denominator in its factored form. So for the first numerator, I have cosine times cosine, which we can rewrite as cosine squared, so cosine squared of theta, plus, from our second numerator, sine times 1 plus sine. So we have to distribute that sine into parentheses. So sine times 1 is just going to be sine, so sine theta. And then sine times sine is going to be sine squared theta. And then all of that is over our common denominator. And again, we want to leave it in the factored form. So cosine times 1 plus sine, just write it in that form. Don't distribute the cosine. And you're going to see why in just a moment. Okay, well, it kind of looks like we made things worse. But as it turns out, we didn't. So we converted everything to sine and cosine. Now when I look at my numerator, that's what I want to focus on at the moment. When I look at the numerator, what I see here are these two squared terms. Anytime I see squared trig functions, that should be a red flag that you may need to use one of the Pythagorean identities. So remember, we had 3 Pythagorean identities related to the Pythagorean theorem, which is why they're named that way. And they tell us how we do things with squared trig functions. So our first Pythagorean identity, the fundamental one, tells us that if we take a sine squared and a cosine squared and add them together, they add up to 1. So even though they're not side by side, they're both still technically being added. We could rearrange the terms in the numerator without changing anything. So cosine squared plus sine squared, based on that Pythagorean identity, adds up to 1. And so that very much simplifies our numerator. So what are we left with? Well, those two terms, again, they add up to 1, and then we have our plus sine theta. So 1 plus sine theta divided by our, again, common denominator. So cosine theta times 1 plus sine theta. Now, based on the point we're at now, you can probably see why it made sense not to distribute the terms or distribute the factors in your denominator. Because look at what we have in the numerator, look at what we have in the denominator. We can't cancel the ones, we can't cancel the signs, but if we treat each of these as a full factor, we can cancel out that full common factor, similarly to what we did here. And so in the numerator, again, we're dividing something by itself, which leaves you with a 1. In the numerator, we're left with 1. In the denominator, we're left with cosine theta. And again, we don't want any fractions at the very end, so we're not quite there, but we know 1 over cosine could also be written as secant. So all of that simplifies down to secant theta. Okay, so what have we used so far? We've used a couple of different strategies. We've substituted in places using an identity. So we wrote secant as 1 over cosine, cotangent as cosine over sine. We used 1 over sine, converted that to cosecant. Tangent was rewritten as sine over cosine. We used a Pythagorean identity here to replace those two squared terms, summed them. They sum to 1. 1 over cosine is secant. So we've actually used several identities so far. Now we also use the strategy of multiplying in the numerator and denominator by the same thing in order to get a common denominator. So that was another critical strategy here. Let's look at another problem that's going to require a slightly different strategy. Now this one looks quite a bit more complicated than the previous two. So our numerator is tangent squared of t minus 1, and our denominator is tangent t times sine t plus sine t. And again, we want to simplify this expression, write the final form with no fractions. Okay, now we could write everything in terms of sine and cosine. The denominator already has some signs, so we're close. So tangent could be written as sine over cosine. Tangent squared could be written as sine squared over cosine squared. We could technically do that, and that might put us on the right path. That might give us some strategies that we can use. The drawback to doing something like that, though, is the fact that we'll then have fractions inside of fractions, which automatically becomes more complicated to simplify. So although it might then give us a trajectory to follow to get to our final answer, some of the algebra that it's going to take to get from that point to our final answer is probably going to be a little bit more complicated than it needs to be. So that might not be as great of a strategy here. Well, one of the strategies that we haven't yet used is factoring. If there's factorization that we can do in the numerator and denominator that results in common factors on top and bottom, then we can cancel them out, as we've already seen. Anytime we have a common factor that matches in the numerator and denominator, that divides out and reduces to 1 and they disappear. So factoring is another option. So if we can factor our numerator and denominator and produce some common factors, well, those can then be canceled out and it'll simplify what we're left with. So what does factoring look like in this case? Well, we're actually going to have to use a couple of different factoring strategies here. The denominator is going to be a little bit more easy. So notice in the denominator we have two terms. The first term has two factors, the second term only has one of them. One factoring strategy is to look for a greatest common factor. In other words, something that your terms have in common. So in this case, if you look at the two terms in the denominator, they have a sine t in common, which means we could factor out, divide out that sine t, and then write it in a factored form with sine as one factor, and then everything that's left over is another factor. So let's do that. Let's take that denominator, factor out that greatest common factor of sine t, which leaves us with a tangent t from the first term, and then sine factored out of a sine just leaves us with a 1. Remember, factoring is the same thing as dividing. We're dividing it out, so anything divided by itself will leave us with a 1. So that's going to take care of the denominator. Now what about the numerator? These two terms don't have anything in common except a 1, and factoring out a 1 does nothing. However, this is a special case. We actually have a difference of squares. It may not be obvious, but if we think of 1 as a 1 squared, we have something squared minus something else squared. So if it's been a little while since you factored a difference of squares, the rule is if you have two terms that are perfect squares and you're taking the difference, you're subtracting them, then this can be factored as a plus b times a minus b, where a and b are the square roots of those terms. They're the terms that are being squared. So in this case, with our numerator, our a is equal to the tangent of t, and our b is equal to 1, because 1 is the same thing as 1 squared. So we have a perfect square minus another perfect square, which means the numerator factors based on this formula. So let's factor it since it is a difference of squares. So it's going to factor as a plus b, so tangent plus 1, tangent of t plus 1, times a minus b, so tangent of t minus 1. Well, how did that benefit us? What did that do? Well, just like I predicted would probably happen, look at what we have in the numerator and denominator. We have a common factor of tangent t plus 1. So because that entire factor is common in the numerator and denominator, we divide that out and it reduces to 1. So what are we left with? Well, in our numerator, we have tangent of t minus 1. In our denominator, we have sine of t. Okay, well, we're not quite there, right? It's better. It's simpler than it was, but we're not quite there because we still have a fraction involved. So what can we do? Well, we can take a couple different approaches here. ultimately we need to get rid of this sign. So anything we could do to get rid of that sign is going to be good. So one option we have here, since we have a difference in the numerator, we have two terms in the numerator, but we have a single term in the denominator. We can split this up into two fractions. Well, why does that help us? Well, we can't do anything with it in this form. Nothing reduces. You can't cancel anything out because there's no common factors. But if you can split it up into two separate fractions, you may be able to work with each individual fraction, and if you can take each of those and simplify them in such a way that the denominator goes away, then you meet the goal of writing the final form with no fractions. Now immediately splitting it up, I see something I can do with that second term, because remember 1 over sine, that is the same thing as cosecant. So let's write the first one as is. We'll leave that one as is. We'll work with it in a minute. But already I'm a little bit better off than I was, because I can write that 1 over sine as a cosecant. Now, tangent over sine. We've got to get rid of that sine. What is tangent divided by sine? Well, looking at it, I don't immediately know. But I do know that tangent can be written in terms of sine and cosine, which means that if I can write it in terms of sine plus that cosine, maybe I can do something with those common signs. We'll see. So I'm going to rewrite the tangent now as sine t over cosine t. And then all of that is divided by sine of t. And of course we still have that cosecant that we already got. Now notice we're using a strategy here that was not really practical to use at the beginning. So at the very beginning, writing in terms of sine and cosine would have put fractions inside of our fractions. But things also would have been separated by addition and subtraction, which would mean any combination you would do would require getting a least common denominator. It would have been very cumbersome here. But the benefit of waiting till this moment to do it is now there's no addition or subtraction involved. It's just one fraction divided by something else. So although we do have something that's a little bit more complex, we have something that we have a strategy to simplify. Because we know anytime we do fractional division, the easiest way to execute that is going to be to keep the numerator as is, change from division to multiplication, and then multiply by the reciprocal of our denominator. So if we're dividing by sine, that's the same thing as multiplying by 1 over sine. And again, we still have that cosecant. Now, we don't want to convert this to cosecant. The goal is to get rid of all of our denominators. So converting to cosecant means we're still left with that sine over cosine. What we can do, though, is cancel that common factor on the diagonal, because it's now a sine in the numerator and then a cosine and sine in the denominator. So that leaves us with a 1 in the numerator and a cosine in the denominator. So 1 over cosine of t minus cosecant of t. And again, we're still not quite there. We still have a fraction, but as soon as I see that, I know there's another way to write that. 1 over cosine could also be written as secant. So this simplifies to secant of t minus cosecant of t. And again, arguably that's a lot simpler than what we started with, so that's a good place to stop. We don't have any fractions, so we've met that requirement, and our expression is now a lot simpler than it originally was. So I want to emphasize now, this will take some practice, particularly if you've never used these kinds of strategies before, you've never really had to do problems like this. It will take some practice. You'll probably find that for a little while, you get kind of stuck in the weeds. You end up trying some things, and it probably feels like you're making things worse than they originally were. Sometimes it takes making them worse in order to make them better. So occasionally you'll be on the right track. It won't feel like you necessarily are, but keep going. Again, when in doubt, if you can convert things to sine and cosine, it may make things a little bit more complicated in the intermediary steps, but having everything in terms of common trigonometric functions may allow you to cancel some things out and then eventually make things simpler than they were. So keep in mind, you will have to play with these for a little while. You may feel like you're getting stuck, and it's possible that you will do something and you will get stuck. That means you start over. It's okay. You backtrack. Try a different strategy. Try something you didn't try before. Just keep at it. It is going to take practice, and it's a skill that you develop over time. Once you become really familiar with those fundamental identities, the reciprocal identities, the quotient identities, your Pythagorean identities, finding strategies to use will be simpler, and you'll start to see things a little bit more clearly than you probably do at the very beginning. So just keep with it, keep practicing it. So we're going to switch gears just a little bit, use some of the same skills that we're using here, but use them in a slightly different way. So for these last three examples, we've just taken an expression, we've simplified it. Ultimately, though, the end point is kind of unknown because, again, simplification, that's kind of a relative term. What simplified means really depends on the goal we're trying to meet. So here, one of the goals was to write everything with no fractions. So once we converted expressions using identities, using strategies like that, we knew eventually we had to get down to something that didn't have a denominator, to where it was everything just in a numerator, no denominators, right? So the end point was kind of unknown at the very beginning of the problem. We just kind of kept working until we got down to something that met our requirement and was simpler than what we started with. There's another way we can do these kinds of problems where the end point is known. And the question is just, how do we get from where we would start to where we would end? In other words, what if I told you that this complicated expression was equal to this? What if I told you that that relationship was true? Well, you can take it at face value, and hopefully you would. Hopefully you'll trust me. Hopefully you'll take it at face value. But good mathematical practice is not to just take things at face value, right? We need to understand why things are true. So what if I told you these things were equal, and I asked you, well, prove it to me, verify to me, show me that those two things are equal? Well, what that would entail is then finding all of these intermediate steps that it would take to take one of these expressions and write it as this simpler expression. What we now have when we take this complicated expression and write it as this less complicated expression is ultimately a new identity. Because notice this expression and this expression are completely general. T is our input, but we don't know what T is. We've shown that in general, regardless of what T is, this expression and this expression will be equivalent. We could plug in any value of T that we wanted, and this expression would have the same value. So what we've essentially established by doing all of these steps and simplifying this complicated expression, we've essentially created a new identity. We've showed that this expression are always going to be equivalent, hence we have an identity. So we can use some of these simplification strategies in order to essentially create new identities from more complicated expressions. We have really basic identities that establish relationships among our trigonometric functions, but we actually have a lot of different identity relationships that we can build off of those fundamental relationships. So the next thing we're going to look at is taking something like this, taking this kind of relationship, knowing that one expression and another are equal, and doing the verification to show that yes, in fact, they are equal. In other words, supplying all of those intermediate steps that we would need to prove that one expression is equal to the other. So ultimately, we're doing proof. We'll call this a verification. So we're verifying other trigonometric identities other than those original ones that we started with. So again, by simplifying a trig expression of any type, we create a new identity from the ones we already have, using all of those simplification strategies. So oftentimes we want to verify that some type of simplification is correct. In other words, if we start with something complicated, we want to verify that the simpler version is in fact equivalent to that more complicated version that we started with. So this essentially means proving that we can get from one side of the equation, typically the more complicated side, to the other using algebra, using those algebraic skills that represent just simplification. not squaring both sides or adding things to both sides, but just simplification strategies, rewriting things in a different way. Now, this is going to definitely require trial and error, but there are some guidelines that will kind of keep you on the right track, just some general strategies to try that will help you get started when it doesn't necessarily seem like you may have a lot of strategies. Now, typically, if you're taking an identity, which again is going to be an equation, it's a relationship between one side and another side that's always going to be true regardless of the inputs. Typically, if you want to show that you can go from one side to the other, that the two sides are in fact equivalent, it's typically easier to start with the most complicated side of the equation. It's easier to take something that's complicated and simplify it than it is to take something that's simple and somehow make it more complicated. If you start with something that's simple and make it more complicated, typically that means you have to supply things that weren't already there. And knowing how to supply things that aren't already there is typically a very complicated, very difficult thing to do. So we're going to start with the more complicated side of our relationship that we're attempting to verify. So one good strategy, look for opportunities to use your fundamental identities, your reciprocal identities, your quotient identities, those kinds of things. Look for opportunities to use those identities to take something and replace it with another expression. So when you're looking at an expression that has products or quotients already, consider using the reciprocal or quotient identities. So we've seen that we could replace 1 over sine with a cosecant. We could replace tangent with sine over cosine. Those kinds of things. Being able to substitute expressions in that way may lead you along the right track to getting from where you start to where you want to finish. Now, when there are squared terms, you might want to consider using the Pythagorean identities, since all three of the Pythagorean identities relate specifically to a trig function that's been squared. Now, if we have a trig function that has a negative argument, it has a negative inside of the function attached to the input, consider using the even and odd identities. So just as review, since it's been a little while, sine, its reciprocal, and then tangent and its reciprocal are all going to be odd functions, and then cosine and secant are going to be even functions. An odd function means we apply the function to a negative input. That's the same thing as the negative of the trig function. Even functions, when we apply our trig function to a negative input, it's the same thing as the cosine or the secant of the positive input. In other words, the negative doesn't matter, it just goes away. Other options, use your basic algebraic techniques. In other words, finding a common denominator, factoring, those kinds of things, those strategies that you use to take an expression and simplify it. And again, just like with the simplification problems, when in doubt, if you're stuck, you're not sure what to do, a good strategy is to convert everything, write everything in terms of sine and cosine. In a lot of situations, your immediate inclination will be to do that. Sometimes it helps, sometimes it doesn't. Sometimes it helps but makes it more complicated, which just means the additional steps it may take to get to the answer you want, maybe a little bit more complicated than they would necessarily have to be. But when in doubt, that's usually a good place to start. So just like with simplification, these are going to be the kind of problems that are going to take a good bit of practice. If this is the first time you've ever applied some of these kinds of skills, proving relationships in general with no numbers involved, it requires a very specific skill set, and it is a skill set that you can cultivate. So the more of these problems you do, you start to recognize patterns. You start to see structural kinds of things. When I see this, this is what I do. When I see this, this is what I do. But ultimately, it's going to take a lot of practice to be able to recognize those kinds of commonalities among the problems you're going to do. So let's work through a few examples. Okay, so again, we're verifying. That means we have a relationship that's already given. That relationship is given in the form of an equation, and we just want to prove that that equation is actually true. In other words, we want to start with one side of the equation and show that just by using legal algebraic techniques, that that one side of the equation can be made to look like the other side of the equation. Now, here is what we cannot do. You cannot take the left-hand side of this equation and the right-hand side of this equation and square them. You cannot do that. That requires assuming that this is true. We're attempting to prove that this relationship is true. We're attempting to prove that we could set these things equal and say that they are in fact equal. Well, you can't prove they're equal by assuming they're equal. That's a logical fallacy. You can't do that. What we have to do is choose one side or the other, and only working with that one side, we have to only manipulate that one side and show that using our algebraic techniques, using our identity substitutions, all of those different strategies, show that we can take this expression and equivalently relate it to whatever this expression is on the other side. So essentially what you're going to have to do is you're going to have to pick one side and just work with that one side. You cannot work with both sides at the same time. Pick one side and then go with it. Now in this case, it's going to be pretty obvious you need to work with the left-hand side. How do you get from a -1 to all of this? Well, honestly, I have no idea how you would do that. You certainly could, because we're saying that these are equal. But starting with -1 and getting here means you're going to have to suddenly supply a bunch of things that aren't there. Whereas if we start with the left-hand side, we're ultimately making it simpler. So making it simpler is going to be easier than making it more complicated. So to start, I'm just going to rewrite the expression I'm working with as is, no changes. Just rewrite it as it's currently written. Okay, and I want to simplify this. The goal is to take all of this and show that it is logically equivalent to -1. Okay, well immediately I see cosine of a negative, tangent of a negative, and I know I'm probably going to have to get rid of those in order to be able to relate it to a trig function that doesn't have a negative input. Well, that's when I'm going to use my even-odd rules. So cosine is an even function, which means that cosine of a negative input is going to be the same thing as cosine of the positive version of the input. That is the rule for an even function. Now, tangent is an odd function, which means that if we take the tangent of a negative, it's the same thing as the negative version of the tangent of a positive input. Now notice I've written the multiplication dot. I would recommend you do that here, because if you just write the negative, it's going to look like you're subtracting, which you're not. You're multiplying a positive term, or what appears positive, by a term that has a negative factor. Or excuse me, they're all factors, but by something that is negative. Okay. Well, we've gotten rid of the negatives. So that's a good start. We're trying to get rid of everything though. All of this should go away, and all we should have left is just a -1. So I see a sine, I see a cosine, I see a tangent. I want a bunch of things to be able to reduce. I want everything to reduce to 1. So if I've already got a sine and a cosine, a good strategy here would be to write our tangent in terms of sine and cosine, since we know that having that sine and cosine we potentially could reduce with this sine and cosine. So I'm going to write my tangent as a sine over cosine. So my numerator is now going to be cosine of x times negative sine x over cosine x. And then of course all of that is divided by sine x. Okay, now in the numerator I have something that's rational multiplied by something that doesn't have a denominator, and I know I can put this over 1 if I want it to have a denominator. The benefit of thinking of cosine in that way is now we have two fractions. One has a numerator of cosine, one has a denominator, which means that common factor divides out, reduces to 1. Which means all we're left with in our numerator is going to be a negative sign. So negative sine x. And then our denominator, we just have sine x. Well, look where we are. We now have a common factor, again, in the numerator and denominator. The numerator is negative, the denominator is positive, which means when we cancel out that common factor, we're left with a negative, and then anything divided by itself is going to be 1. And that is exactly where we want to be. So using only legal algebra, using only simplifications and substitutions, we verified that the left-hand side of this relationship is in fact equal to the right-hand side. So that essentially proves this relationship. And again, notice this was entirely in general. We don't know what x is. So what this tells us is that this relationship is true in general. In other words, we could sub in any value we wanted for x as long as all three of these functions were defined, and this whole expression, regardless, would reduce down to -1. Okay, so as we go, let's sort of make a list of the identities, the strategies we use, just so you have a sense of what we're doing each time. So what did we actually do here? Well, we needed the even-odd rules. So we used the even and odd identities. Okay, we used a quotient identity. And past that, it was really just reducing common factors. Anything divided by itself is 1. So those would be the major things we used here. We used a couple different types of identities. Okay, let's look at another example. Stepping up a notch, slightly more complicated. So we want to verify that 1 divided by 1 minus cosine x minus 1 divided by 1 plus cosine x is equal to 2 times cotangent x times cosecant of x. Okay, now again, start with the more complicated side. Sometimes one side versus the other, they look relatively similar in terms of complexity. Here, I would argue that the left-hand side is more complicated. Typically, the side that has addition or subtraction versus a side that doesn't will be considered the more complicated side. So in this case, we want to work on the left-hand side and convert it so that it's equivalent to the right-hand side. So I'm going to go ahead and just rewrite it. So 1 over 1 minus cosine x minus 1 over 1 plus cosine x. And we're just going to work with this one side. Now again, we can't square both sides, we can't divide out the 2, we can't do anything like that because that requires assuming equality. Our goal is to prove equality, which means only working with one side at a time. All we can do is algebraic techniques that don't require doing something to one side and doing something to the other at the same time. Now at the very end, I know there's no addition, no subtraction. So the fact that there are 2 terms subtracted is a problem. I need to somehow combine those. So that's probably where I'm going to start. I need to combine these together. Now in this case, we have different denominators. So combining them together is going to require that we get a common denominator first. Now, we have to treat each of these as a full factor. You may be looking at these and saying, well, they basically are the same. We just have a positive versus a negative. But you have to treat this as an entire factor. If we treat these as individual factors, the 2 factors are different, which means our common denominator is going to require both of them. So for our first fraction, we're missing the 1 plus cosine. So I'm going to multiply in the numerator and balance it by multiplying in the denominator by that factor that we're missing. Now in the second term, for that second ratio, I'm missing my 1 minus cosine, so I'm going to multiply on top and bottom by 1 minus cosine of x. And let's see where that leaves us. Now, as we discussed with the simplification, it's a good idea to just start by leaving the denominator in a factored form in a lot of cases. But in this case, the denominator is going to be combined in a very specific way. Having these 2 factors multiplied together results in a very specific combination. It's actually a reversed difference of squares, so this is a factored version of a difference of squares. If we FOILed out these 2 binomials multiplied together, 1 times 1 is 1, minus cosine plus cosine, those cancel, and so then we have a negative cosine squared. So because this is so specific, I am going to go ahead and I'm going to combine those together. So what do we have in our numerators? Well, for the first numerator, we have 1 plus cosine x times 1, which we don't have to write. And then from that, we are subtracting, so watch your signs, subtracting 1 minus cosine of x. And then all of that is divided by our common denominator. And again, we're going to FOIL it out, and we end with 1 minus cosine squared x. So let's clean up our numerator. What do we have? Well, 1 minus 1 equal and opposite. They cancel. Now be careful with the other two terms. We have a positive cosine minus a negative cosine. Those double negatives will convert to an addition. So cosine plus cosine is going to give us 2 cosine. So our numerator is going to be 2 cosine x. And then our denominator is going to be 1 minus cosine squared x. So where are we so far? It's a good idea to check in with the original identity, what you're trying to verify from time to time, so you see how far you are away or how close you are. Think about the kind of things that are in the final answer we want, and maybe what's already there versus what we still need to get. Well, I see this 2, and I see a 2 here, so I know that 2 is probably the same one as the one we want to end with. So that's good. I'm getting there. I want a cotangent and a cosecant, but I've got a cosine. I've got 1 minus cosine squared. Well, when I see a cotangent, I know cotangent is the same thing as a cosine divided by a sine. Well, I've already got a cosine right here. I just don't have a sine down here. So more than likely this cosine will also need to be here, at least for the next couple of steps, because I know if I can get a sine in the denominator, well, the cosine and the sine will take me to my cotangent. So I'm going along the right track. The problem here right now is this 1 minus cosine squared. This is not represented anywhere here in our final answer. But what I see when I see this is, again, a Pythagorean identity. Anytime I see a trig function squared, that is a red flag that we may be using a Pythagorean identity. Now, this does not immediately match a Pythagorean identity. But what's the identity involving cosine squared? Well, the identity involving cosine squared is that sine squared plus 1, or excuse me, sine squared of x plus cosine squared of x is equal to 1. There we go. This equation is true. We assume this is true, and we actually showed it was true in a previous video. What that means is that any version of this is true as well. In other words, if I rearrange this equation, I'll also end up with a true equation. So I have the expression 1 minus cosine squared. Notice if I subtracted a cosine squared from both sides using this identity that we know to be true, I would end up with sine squared is equal to 1 minus cosine squared. So what that tells me now is that using this alternate form of the identity, 1 plus cosine squared could be replaced with sine squared. So I'm going to take the 1 minus cosine squared, which again is not represented in my final answer that I want, and I'm going to replace it with sine squared, which is going to be a little bit closer to what I want, because remember, cotangent, that would be cosine over sine. Well, if I can get this sine squared here, I'm going to be on the right track. So I'm going to replace that denominator using that alternate version of that Pythagorean identity. So the new denominator is going to be sine squared of x. Well, sine squared, that's the same thing as a sine times a sine. So I've got my 2, I've got a cosine over a sine if I take only one of those sines. Well, that'll leave me with another sine in the denominator. So I want to split things up at this moment and see if we can split it up and maybe get a little closer to where we are at the end. At the end, we have 3 factors. We have a constant factor of 2, and then the other 2 factors are going to be trig functions. So let's see if I can split this up and make it so that it's a little bit closer to where we want to be. Well, we've got the 2, So I can pull that out. Keep in mind anything in the numerator could just be written over 1. Just pull it out, leave it where it is. Well, we have a cosine, and if we just take one of the signs in the denominator, we could write that as a cosine x over sine x. That's completely legal to do because we're just taking something that's squared and we're writing it as sine x times sine x. Legal to do. And so I'm just pulling off individual factors as needed. So cosine over sine, well, that takes care of everything in the numerator, which means the only thing we'd have left in the numerator is 1, but in the denominator we still have another sign. So we could also write another factor of 1 over sine x. And look where that takes us. We have a 2. Cosine over sine is the same thing as cotangent. And the leftover that we maybe weren't sure about, well, 1 over sine is also equivalent to cosecant. And so based on the quotient and reciprocal identities, we have 2 times the cotangent of x times the cosecant of x. And that verifies our identity. So what all did we use here? Well, we used some additional strategies. First thing we had to do was find a least common denominator. So we found a least common denominator. Okay, we just did some reduction, combined some like terms. Well, down here we used a Pythagorean identity, just an alternate version of it. We rearranged that Pythagorean identity and used an alternate version. And then we used, let's see, we used a quotient identity, we used a reciprocal identity. So we used a quotient identity, and we used a reciprocal identity. And then of course just some other basic algebra techniques here and there. So that's everything represented there, and again, that identity is now verified. Okay, let's look at a couple more. Situations where we might use other strategies. Okay, so we want to verify that 1 minus sine t divided by 1 plus sine t is equal to the quantity secant t minus tangent t, all of that squared. So again, both sides look relatively complicated here. In that case, I would probably start with the side that involves a ratio. It's easier to get rid of a ratio potentially than it is to create one where there wasn't one already. And I already know that the left-hand side has sine, so working with sine and cosine tends to be easier. So I'm going to start with my left-hand side. 1 minus sine t over 1 plus sine t. Okay, some things that are tempting to do that we cannot do. We cannot cancel the ones, and we definitely cannot cancel the signs, which would be very tempting to do. You have to cancel a factor in its entirety. These individual things are terms. The entire numerator is a factor, the entire denominator is a factor. Because the factors don't match, nothing here reduces. So in its current form, we can't do anything with it. So here is another strategy we can use. Kind of like the strategy we used to get the least common denominator. We multiply top and bottom by the same thing. We're actually going to do that here as well. Specifically, we're going to take the denominator and we're going to multiply by the conjugate, what we call the conjugate of the denominator. So the conjugate is going to take the same two terms, but this addition is going to be written as a subtraction. That by definition is the conjugate. So I'm going to multiply in the numerator and in the denominator by the conjugate of the denominator specifically. So 1 minus sine t is the conjugate of our denominator. And in order to keep things in balance, I have to do the same thing on top that I did on the bottom. So I'm going to multiply in the numerator also by a 1 minus sine t. Okay. So where does this take us? What does this do for us? Well, in the numerator, let's just write what we literally have. We have 1 minus sine t, and notice we multiplied it by itself. The numerator matched with what we multiplied, so I'm going to write that as 1 minus sine t squared. Now in the denominator, This is kind of like one of the previous examples that we had, where we had factors that looked like this, they were structured like this, and when they distribute in a very specific way. So 1 times 1, and the negative sign and positive sign will cancel. Positive and negative is a negative. Sine times sine is sine squared. So we could also write this as 1 minus sine squared of t. Okay, and right now it doesn't seem obvious where we're really going from here. Okay, there's still a lot left to do. Now, if I look at the very end though, I see a secant, I see a tangent. What if I were to write these in terms of sine and cosine? Well, secant would be 1 over a cosine, tangent would be a sine over a cosine. So because there's that common cosine that would be in the denominator, if we were to rewrite both of those, that's a good indication that somehow I need to get a cosine in my denominator. Well, as of right now, I have a 1 minus sine squared. Okay, but if we flip back, let's look at the previous example we did. This is kind of similar to a situation that we were just in the previous example, right? Right down here, 1 minus cosine squared. We replace that with a sine squared using an alternate version of our Pythagorean identity. Well, in this problem, we have 1 minus a sine squared. So imagine taking that Pythagorean identity, and instead of getting 1 minus cosine squared, what if we got a 1 minus sine squared? What if we subtracted the sine squared from both sides? Well, that would leave us with a cosine squared. So cosine squared is going to be equivalent to 1 minus sine squared, which is what we have right here. And again, at the very end, it looks like we're probably going to need a cosine in the denominator based on the kinds of things we have at the very end. So replacing that 1 minus sine squared with a cosine squared is going to be a really good strategy to use here. So we have 1 minus sine of t squared, and then using that Pythagorean identity, we're going to replace our 1 minus sine squared with a cosine squared. Okay, so we're getting there. We're on the right track. Now, we're also to the point where it looks like we have 2 terms. We have a denominator of cosine. We have 2 terms. Both could be rewritten with a denominator of cosine. So we're definitely on the right track. Now, I notice here with this final expression, it's one factor and the whole factor has been squared. Okay, so it's almost like kind of factoring out the exponent. That's not quite what it is, but it's kind of what it looks like. Well, as of right now, I have a numerator. The whole numerator is squared. And I could also think of this denominator as being a cosine of t squared. I could also think of it that way. So because the numerator is one factor squared, and the denominator is also one factor squared, one of my algebraic rules, specifically a rule for exponents, says I could rewrite this as one big factor with a numerator and denominator, the whole thing squared. So again, think of it kind of like factoring out the exponent. That's not really what we're doing, but it looks kind of like that. We're pulling out the exponent that's common in the numerator and in the denominator. Well, how does this benefit us? Well, again, we get a little bit closer to where we were. We have one whole factor with 2 terms, and the whole factor is squared. Well, believe it or not, we're almost there. Now that I have a single term in the denominator, I can split up my numerator and write each of the terms in the numerator over that denominator. So this expression could be rewritten as 1 over cosine minus sine over cosine. So let's see where that takes us. So we have 1 over that common denominator of cosine minus sine, and I just changed to x, that should be a t, sine over our denominator of cosine, and again, all of that was squared. Well, we're about there. Look where we wanted to go. We wanted a secant, we want a tangent. 1 over cosine, well, that's our secant. Sine over cosine, that's our tangent. So using that reciprocal and quotient identity, we can get down to our final answer. And there we go. So what strategies did we use here? What identities did we use? Well, the first strategy that was unique to this problem, we multiplied by the conjugate, specifically the conjugate of the denominator. That'll typically be the case. Typically when you use this conjugate strategy, it's going to be the conjugate of your denominator. And so the benefit of multiplying two factors like that is when they multiply together to give you a difference of squares. And in this case, that's just a rearranged version of one of our Pythagorean identities, which leads us to the next thing we used. We used, again, that same Pythagorean identity, just rearranged, used in a different way. Okay, this next step, again, we kind of sort of factored out our exponent. Again, that's not quite what we're doing, but it looks kind of like that, pulling out that common exponent. We split it up using just a general algebraic rule, and then we used our reciprocal and quotient identities. So reciprocal and quotient identities. You're going to find those a lot. Use those two kinds a lot. And that got us down to our final answer. Okay, let's try one last example. This will definitely be the most complicated one. Now, with this particular example, I would argue that both sides look complicated. So the side you choose to start with, I mean, it really is up to you. In this case, it's just going to be which side do you feel like you have a strategy for. So when I look at this one, and I look specifically at the left-hand side, that left-hand side makes me think of a lot of what this left-hand side looked like. Structurally, it's very similar. So one term plus another, one term minus another, where those are the same terms. Well, structurally, that's basically what we had here. And we multiplied by the conjugate, and that seemed to be a good strategy. That seemed to help us out. Now, when I look at the right-hand side, nothing immediately stands out that I can do. Everything's already written in terms of sine and cosine. I can't really split anything up. Well, 1 minus 2 cosine squared, that doesn't represent anything involving one of the Pythagorean identities. It would have to be just 1 minus cosine squared. So I don't really feel like I have a good strategy to start with on the right-hand side. So I'm going to work on the left-hand side instead. Now, that being said, as I mentioned before, you will potentially find that you try something and it feels like it's just not working. You're getting kind of stuck in the weeds. That will happen. More than likely, it'll happen more than once. And that's okay if it does. That may mean you want to try working with the other side, and something may just pop up that seems to click, that seems to work. It's really just going to depend on the situation. You're going to have to be patient. You're just going to have to practice. You're going to have to be flexible and be willing to start over if you just find you're getting further and further down the rabbit hole and nothing's really happening. And again, it's just going to be really more than anything a matter of recognizing strategies based on the structure of what you're looking at. So these situations where we have a numerator and denominator that are almost the same but maybe differ in a sign, that may be an indication that multiplying by the conjugate is going to be a good strategy to use. And again, it's typically going to be the conjugate of the denominator. So in this case, the conjugate of sine minus cosine is going to be sine plus cosine. So I'm going to multiply that on the bottom, but in order to balance it, I also have to multiply by the same thing on top. Okay. So with the previous one, that's exactly what I did. And I ended up leaving the numerator undistributed, but I did so because at the very end I knew I was going to have two things subtracted that were squared. So leaving it as two things that are subtracted and squared seemed like a good strategy there, just based on the form that I expected for my final answer. Now, I don't see anything like that here. There's no parentheses at the very end, which means that more than likely I don't want any parentheses here as I'm working. So I'm going to go ahead and distribute out everything. The numerator I'll distribute, the denominator I'll distribute as well. And again, keep in mind the denominator distributes in a very specific way. So in the numerator, we're going to have a sine times sine, which is going to be a sine squared. Now my outer pair is sine cosine, and my inner pair is also sine cosine. It's not equal and opposite, it's a positive and a positive, which means we're going to combine, and there's going to be two of them. So 2 times sine times cosine. And then my last pair is going to be cosine times cosine, and again it's going to be positive, so cosine squared of x. Now what about the denominator? We're going to have sine times sine, which is sine squared. As with the other times we've seen this kind of form, the outer pair is a positive sine cosine, the inner pair is a negative sine cosine, so equal and opposite, they're going to cancel. And then the last pair, cosine times cosine, but it's going to be negative. So minus cosine squared of x. Okay, let's focus on the numerator for a moment. Where do I want to be? I want to have 1 plus 2 sine x cosine, and there should be a little x right there. I was cut off. Well, I have 2 sine x cosine x. I've already got that part. I don't have the 1. But notice I've got a sine squared plus a cosine squared. We know those add together to give us 1. Now, I don't see anything specific with the denominator. Be very, very careful here. We have sine squared minus cosine squared. That does not combine to 1. That is not the same thing. They have to be added together to combine the 1. If they're subtracted, there is not an identity that tells you what that is. You can't do anything with that. So I'm going to go ahead and just clean up the numerator, and then we'll see what we can do with the denominator in just a moment. So 1 plus 2 sine x cosine x, and I have the numerator I want, so I am done with that. The numerator is good. So that means any other strategies I choose to use, I need to make sure that they don't impact the numerator, because the numerator is where I want to be already. But what about the denominator? Not quite there. Well, let's look at what we want. We want 1 minus 2 cosine squared. Well, we've already got 1 cosine squared. We want it to be negative. We've already got 1 negative cosine squared. So ideally, that needs to stay since it's part of what we want for our final answer. The sine squared is where we have a problem. So how could I take that sine squared and from it get a 1 and get something involving cosine squared? Well, again, this is going to be another great time for me to use that Pythagorean identity. We know that sine squared plus cosine squared is equal to 1. We've now used that identity a couple different times in different ways. Well, here I have a sine squared that ideally I would like to get rid of. If I were to take this identity and subtract a cosine squared from both sides, we end up with a sine squared is equal to 1 minus cosine squared x. So notice I can now substitute something in place of sine squared, knowing this identity is true, knowing this form of it will also be true. I can substitute a 1 minus cosine squared. And what's the benefit of that? Well, we now have another cosine squared, and we'll also have the 1 that we need. So I'm going to replace this sine squared using that identity. And again, our numerator is right where we want it to be, so we're not going to do anything else with the numerator. We're going to leave that as is. But our denominator, in place of our sine squared, we're going to put that rearranged version of our identity relationship, 1 minus cosine squared. And then we already have the other negative cosine squared. Well, we have the 1 that we want, and we wanted negative 2 cosine squared. Well, here's a negative, they combine to give us negative 2 cosine squared. So we already got the numerator we wanted, and then our denominator, we have our 1, and then we'll have a negative 2 cosine squared x. And that is where we want to be. So what strategies did we use here? Well, again, we used the conjugate. That's how we started the problem. Okay, we distributed everything out. We used a Pythagorean identity. Now this is kind of interesting though. Look how we use that Pythagorean identity. We actually used it twice, but we used it in two different ways. So the first time we used it in the fundamental form. We took sine squared, added it to cosine squared, and we know that's equivalent to 1, which is just the identity in its basic form. In this next step, we used it in the denominator, but we used an alternate form in order to replace one of the terms in the denominator. But it was actually the same identity in both cases. It was just a rearranged version of it. So we actually used that same identity twice, just in two different ways. So once we replaced that, past that, it was just basic algebra, combining your like terms, and then going from there. So that gives you sort of a general idea of the kinds of problems you might see, the kinds of strategies you may use. We're going to continue to add on to our list of identities. So different structures will have different strategies, different identities to handle those different situations, depending on the types of expressions and the types of more complicated identities we want to verify. So again, I just want to emphasize one more time, these are complex problems, particularly the first time you approach these kinds of problems. Many people tend to struggle with them, and that's okay because it requires a very different skill set than the skill set that just basic algebra requires, graphing requires, those kinds of things. So you're primed with those kinds of skills at this point in your math career. These kinds of skills, these very abstract proof kinds of skills, typically you don't have as much experience with this at this point. So it will take some practice, and it's okay if you don't get it the first time. If you find that you're trying some techniques and they just don't seem to be working, backtrack, see if there's maybe somewhere you made a mistake. That's always possible. Maybe the strategy you're using is just not a good option. Go back to that list of strategies. We talked about some of the general options you have in different situations. See if you can try a different strategy, and that may put you back on the right track.